Thank you for that introduction. So we're back to Lattice Boltzmann methods, quantum Lattice Boltzmann methods to be precise, but we're going to approach them from a slightly different perspective. So this time we're going to talk a little bit about the implementation of these algorithms, both in terms of future quantum computers, but also in terms of what we can do today with the hardware that we have available. So a little bit of a roadmap first. So I'm going to very briefly introduce the Boltzmann methods, or that is Boltzmann method both classically and the quantum version, and then just as a reminder, and then motivate the purpose of software in this environment. So the main thing that we need to worry about in the Boltzmann equation is this distribution function f. So this lives in a 7-dimensional space, 3 physical dimensions, 3 velocity dimensions, and time. And it evolves with, well, time as well as velocity with respect to space and external forces. And of course, we need to discretize this along all 7 dimensions. So we select some discrete velocities that particles can move about in space. We discretize the space into a grid, and then we also take discrete time. And here we perform some kind of collision operator. In this case, this is the very widely used BGK. There are many choices that you can make at every point in this discretization procedure. So you can go for different velocity sets, different equilibrium functions. So this is the third equation. You can go for different collision systems, but we're always concerned about this F function. And again, the classical LBM loop is sort of a 3-stage process where particles first move throughout space. So they stream, then they collide, and finally, there's some boundary conditions that we apply at the edges of obstacles. So this is what the discretization looks like. Again, particles can just move across some of these channels across the 3 dimensions. So this makes it easier to solve on well, any kind of computer. So again, very briefly, the motivation for quantum CFD, we've already seen it several times before, so I'll just quickly mention that here we can achieve a lot of memory compression. So n qubits can relatively straightforwardly encode 2 to the n classical bits. And then with quantum parallelism, there is also the opportunity for manipulating the entire quantum state in one go with each operation, which opens the potential for some better performance. But we're not there yet. So quantum CFD is, as far as my opinion is concerned, a long-term project, especially if we try to achieve what we're doing here, which is do it fully, so end-to-end on the quantum computer. The algorithms that we're developing are really fault-tolerant or nothing. So in this case, the quantum hardware is still unreliable. There's still a lot of noise, and the algorithms still have a long way to go before we can have any sort of substitution for the classical methods of today. So this is quantum CFD, but this talk is about software. So why is software relevant in this environment? Well, we've learned from the classical world of Lattice Boltzmann methods. There are many successful parallel implementations. We see them in academia, we see them in industry as well. And we also know that open source software tends to be very successful at accelerating collaboration and research. So classically, the Lattice Boltzmann method is quite a mature piece of a software, many different branches, but this is not the case for the quantum alternative. So the quantum LBM software implementations that I'm aware of, at least there's only one paper that came out 2 months ago. It is not yet open source. So there's still a lot of room for improvement in terms of what we can do to bring more people to this field and make it accessible. So this is about software in general, but we don't just write software for the purpose of catching up to the classical LBM. We want to solve several problems, specifically 4 of them. So if we're interested in making this a long-term project that's successful, we want to be able to implement and extend quantum Boltzmann methods, which at the level that quantum programming is right now is extremely tedious. So even if someone were to hand you an algorithm end-to-end and you just wanted to extend it by some little bit of technology, that would be very difficult to do and generalize because the programming level is so low. So modularity is one thing that we try to achieve. Second of all, like I mentioned, the long-term vision for this project is to reach fault-tolerant computing. So in the meantime, we still want to be able to develop and pursue research without fault-tolerant hardware, which means we rely on simulation, which is inherently slow because of the exponential memory advantage that quantum computers have, which we need to emulate. So software needs to be fast. Like I said, even coming up with the smallest piece of quantum Boltzmann methods, anything really is very difficult, and generalizing it is a challenge. So we wanted to build accessibility. And finally, we also have to think about the larger software environment around quantum computing. So quantum software has been rapidly evolving, and we want to take advantage of that to the biggest extent that we can. So those are the four things that we want to achieve: modularity, performance, accessibility, and integration. And to that end, we developed this software package, which we very creatively called QLBM, Quantum Lattice Boltzmann Methods, which aim to be an end-to-end environment for developing, simulating, and analyzing these algorithms. So next, I'm going to talk about how we try to solve these four problems, or how the solutions that we built into QLBM for those four problems. But before that, I just want to first bring some context as to what quantum programming is like at the moment. So first, I'll draw this comparison to classical programming or classical computing, where you generally start from some high-level piece of code. So here I have a C++ example, but you might even go a level higher and rely on some code generation tools. Then you go on to choose a compiler, which then gives you some much lower level code, which you give to your hardware, whichever it may be, CPU, GPU clusters, it doesn't matter. This flow is something that everyone is used to in the CFD space and beyond, and we want to learn from this. The quantum alternative is quite different. So as to the classical situation, we would rely on these high-level programming languages that have been decades in the making. If you want to implement a quantum algorithm, you're still limited to, well, here I call them high-level circuits, but I like to think of it more as programming in quantum assembly. So you still have to place individual gates on individual registers by hand to build up a quantum algorithm. The rest of it, though, is fairly similar. So you still have your compilers that take your sort of, well, so-called high-level circuits and turn them into hardware-specific alternatives. So much like classical hardware, quantum hardware have gate sets and topologies that you need to take into account when transpiling a circuit. And then here I very optimistically chose a quantum computer as the hardware which you would run it on, but of course you have simulations. So this is what QLBM tries to target. It tries to take this, this workflow, let's call it, and improve it, bridge the gaps where quantum computing still has to catch up to classical. So this is how QLBM does that. So the first problem we had was we were starting from this very low level quantum assembly, like I call it, these quantum circuits that you have to build by hand. In QLBM, you start from a much higher level of a system specification. So you just need to tell the software, I want a grid of this many grid points in this dimension with this many velocities, this geometry, and so on. And what QLBM will do for you is it'll take this configuration and parse it automatically into this high-level quantum circuit. So you never have to worry about writing this by hand. The software does it for you. Next, again, QLBM has built-in support for different compilers, so you don't have to learn this to do this yourself. You can just say, I want this specific piece of compiler software. Out comes the hardware-level circuit, so this is no different. From this, QLBM again bridges the gap between this low-level circuit and current hardware, so you can choose a running platform. We have support for Qiskit by IBM and QLEX by Fujitsu. And then you can go onto your piece of hardware. So again, simulators on processors, GPUs, or and hopefully in the future, fault-tolerant quantum computers. But it doesn't end there. We can still go one step further and parse the results that you get from your hardware into the visualizations that we're used to seeing with classical CFD. And finally, there's also analysis tools that to help you monitor and reason about the performance of your algorithms, both as a simulation, as well as in terms of theory. So this is the workflow that we have built. And next, I'm going to zoom in a little bit into how we solve those 4 problems that I mentioned earlier. So as far as modularity is concerned, we have an abstraction pyramid that helps you build quantum circuits more easily in a way that's more verifiable and extendable. So this is in increase in terms of complexity, where at the very bottom, we have the building blocks of quantum computing, the gates and the registers. A level up from that is what we call primitives. So these are small parameterized quantum circuits that you might want to reuse throughout your quantum Boltzmann methods in different places with small tweaks. A level above primitives, we have operators. So if you put many primitives together, you get something that performs some kind of physical operation. So perhaps streaming or collision, boundary conditions, and so on. And then if you chain these operators together, you choose a streaming operator, you choose a collision operator, and so on, you get an end-to-end quantum Boltzmann method in the form of a quantum circuit. So I won't go into the details of this. This is more just to illustrate what a primitive might look like. And I just want you to sort of squint your eyes and just briefly look at the structure of these 2 circuits, which are very similar. So if you're to implement something like this and use it in 2 different places, you would want the kind of implementation that you simply switch a parameter and you get the appropriate quantum circuit for your system without having to implement it by hand each time. So this is the kind of advantage that modularity gives you. So next is performance. So like I said, simulation is inherently slow. So for performance, I'll just illustrate one of the standard examples that we have, which is simulating n steps of a quantum Boltzmann method. So if you want to do 1 time step, you just start with some initial conditions. You move on to the time step circuit, so this actually performs the computation, and then you might want some post-processing, and finally you measure at the end. All good. If you wanted to do 2 time steps, more of the same, initial conditions. This time you have to repeat the circuit twice, post-process and measure again, and then you see where this is going. If you want n time steps, the circuit gets bigger, you need to repeat it n times, and then post-process and measure at the end. And this would work fine on a quantum computer, but since we are in the era of simulators and we don't have fault-tolerant quantum computers, we can take advantage of that and do better. So what we have in QLBM is something that takes the initial conditions and then runs a loop over the time step circuit, whichever form that may take, taking so-called snapshots of this quantum circuit as it goes on. So instead of having to do n different versions of this n time steps, you can just do it once, take the snapshots, do the post-processing and measurement afterwards, and basically reduce the complexity from quadratic to linear, which in practice makes a huge difference. It takes simulation times from hours to minutes. And then we have more performance optimizations that I won't go into right now. And finally, the last thing that I want to talk about as far as features are concerned is accessibility. So like I mentioned, we want to make this easy to pick up on. So this is what the QLBM configuration looks like. You can just simply say, I want a 16 by 16 grid, this many velocities. Geometry is just as easy to specify as well. So you just specify the bounds in each dimension, the kind of conditions you want, so specular or bounce back, and that's it. The software does the rest. So again, I won't go into the details here, but this is all Python, so it's all high level. You just need to build a specification of your system. You choose your algorithm, you choose the simulator that you want, and a few more parameters. You can simply load the lattice by specifying its name, and everything is automatically done for you. Running, again, just as easy. You simply run for a number of time steps with a number of shots per time step. Everything else is automated under the hood. So finally, a few examples of what this software can do for you right now. So I've already shown this example in ParaView, or Matthias has shown this example previously in ParaView, where you can specify multiple cuboid geometries and visualize the float field. This takes advantage of the performance optimizations. You can do things that you wouldn't be able to do effectively on a quantum computer. You can scale up both in terms of grid and geometry conditions. So again, each obstacle here, you can have different kind of boundary conditions. And then we also have support for 3 dimensions. So this is really pushing the complexity of the quantum circuits that the software can generate for you to implement all of the edge cases around the cube like this there are around 80 different primitives that perform reflection. And finally, the performance analysis is also there, so you can analyze how your algorithms scale, for instance, with geometries, grid refinement, velocity fields, and so on. And you can also analyze performance. So here, if you take, for example, the green line, you can see the performance of the naive implementation that I mentioned is roughly quadratic, while the performance optimized one is straight linear. So this is the end of what I wanted to show you. I'm just happy to announce that this is also open source as of yesterday. So specifically for ParCFD 2024. So check it out if you're interested. We're happy to collaborate. And thank you very much for having me.
Thank you very much. I guess I appreciated your presentation. I think that's a good push to go in the software direction. So are there any questions? I will start. So it's a big one, I'm sorry. What's your take on debugging quantum computing software?
So my take is debugging quantum software is extremely hard. It's harder than with debugging even low-level programming language like assembly, in my opinion, because the circuit that performs this specific example that I have on the slide right now is something like tens of thousands of gates deep, and none of it is very obvious. So placing one gate in the wrong register can lead to behavior in the quantum state that you wouldn't expect, because it's very hard to reason about tensor products in terms of gates, especially in circuits that are this deep. So I think the two most important things here to take into account when building software are one, modularity, which helps a lot with the stability and isolation. So if you build something new, you should be able to isolate it and make sure that it really works through all of the edge cases. And second is performance. So even if you put it together end to end, and then one of the, in this case, 80 edge cases is wrong, you might have to run it 10, 15, 100 times to figure out exactly what goes wrong. And reducing the performance or increasing the performance such that simulations take even a few minutes shorter can have a huge impact. Those are things that are really important.